Dear students, in this video we are going to study about resistivity, the resistors which are connected in series and also in parallel, and about the color codes of the resistor which are connected in electronic circuits. Dear students, in this video we are going to study about the resistivity, resistors connected in series and also in parallel. Now let us first study about resistivity. In the previous section we have seen that the resistance R of any conductor is given by the expression R is equal to L by sigma A. So this sigma is called the conductivity of the material, and it depends only on the type of the material used but not on its dimension. The resistivity of a material is equal to the reciprocal of its conductivity, that's given by rho equal to 1 by sigma. So rewriting the equation 2.18, using the equation 2.19, we have R is equal to rho into L by A. This L is the length of the conductor and A is its area of cross section. So this resistance of a material is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. The proportionality constant rho is called as the resistivity of the material. And if L is equal to 1 meter and A is 1 meter square, then the resistance R will be equal to rho. Therefore, the electrical resistivity of a material is defined as the resistance offered to a current flow by a conductor of unit length having unit area of cross section. What is the SI unit of rho? That is given by ohm meter, that is sigma m. Based on the resistivity, materials are classified as conductors, insulators, and semiconductors. Therefore, there are three types of conductors. The conductors having lowest resistivity, the insulators, have highest resistivity, and semiconductors will have resistivity greater than conductors but less than insulators. The typical resistivity values of some conductors, insulators, and semiconductors are given in this table. For pure water, it's about 2.5 in 10 power 5 ohm meter. And for semiconductors, the resistivity will be for 0.46 and 640 for germanium and silicon respectively. And for conductors, these are the values. Then we are going to study about the resistors which are connected in series and also in parallel. An electric circuit may contain a number of resistors which can be connected in different ways. And for that we can calculate the equivalent resistance produced by a group of individual resistors. The first case, let us consider the resistors are connected in series. When two or more resistors are connected end to end, they are said to be connected in series. The resistors could be simple resistors or bulbs or heating elements or some other devices. So here in this diagram 2.9a, there are three resistors R1, R2 and R3 which are connected in series. The amount of charge passing through the resistor R1 must also pass through the other two resistors R2 and R3 since the charges cannot accumulate anywhere in the circuit. And due to that reason, the current I passing through all the three resistors will be the same. According to Ohm's law, if same current passes through different resistors of different values, then the potential difference across each resistor must be different. That means the potential difference across the three resistors will be about V1, V2 and V3 across each of the resistors. Therefore, we can write V1 as IR1, V2 as IR2 and V3 as IR3 as same current passes through all the three resistors I. But the supply voltage V must be equal to the sum of the voltages across each resistor. That means V is equal to V1 plus V2 plus V3. That can be written as IR1 plus IR2 plus IR3. And taking this I out, we can write the equation as V is equal to I into R1 plus R2 plus R3. That gives V equal to I times RS. That is, RS is called the equivalent resistance. So RS can be written as R1 plus R2 plus R3. When several resistors are connected in series, the total or equivalent resistance is the sum of the individual resistances. We should note that the value of equivalent resistance in series connection will be greater than each individual resistance. Next, we are going to study about the resistors which are connected in parallel. The resistors are in parallel when they are connected across the same potential difference as shown in 2.10a, like this. So there are three resistors R1, R2 and R3 which are connected in parallel to the potential difference. In this case, the total current I that leaves the battery is split into three separate components. That is, I will be split into I1, I2 and I3 through the resistors R1, R2 and R3. And due to conservation of charge, the total current in the circuit I is equal to the sum of the currents through each of the three resistors. That is, can be written as I1 plus I2 plus I3. And since the voltage across each resistor is the same, applying Ohm's law to each resistor, we have I1 equal to V by R1, I2 equal to V by R2, and I3 equal to V by R3. So substituting these values in the equation 2.24, we can write this expression as I equal to V by R1 plus V by R2 plus V by R3. So taking V out, we can write it as V into 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, I can be written as V by Rp. And here this value Rp, that is called the equivalent resistance of the parallel combination of the resistors. So 1 by Rp can be written as 1 by R1 plus 1 by R2 plus 1 by R3. Thus, when a number of resistors are connected in parallel, the sum of the reciprocals of resistance of the individual resistors is equal to the reciprocal of the effective resistance of the combination. We should note that the value of equivalent resistance in parallel connection will be lesser than each individual resistance. The household appliances are always connected in parallel, so that even if one is switched off, the other devices could function properly. So in the household electric connections, we are following only parallel connection. Next, we are going to study about the color code for carbon resistors. These carbon resistors are looking like this, which can be used in electronic circuits. And here the carbon resistors consists of a ceramic core on which a thin layer of crystalline carbon is deposited, as shown. These resistors are inexpensive, stable and compact in size. And to know the value of the resistances, we can use the color rings. They are used to indicate the value of the resistance. Three colored rings are used usually to indicate the values of the resistor. First two rings are significant figures of resistances. The third ring indicates the decimal multiplier after them. And the fourth color, silver or gold, is represented to know the tolerance of the resistor. So here you can see the three colored rings. The first ring shows the first digit. The second one is the second digit, second color. The third color is the decimal multiplier. And the fourth one is the tolerance of this resistor. And here these are the color codes for the resistors: black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver, and colorless for tolerance. So you can remember the order of the number by using the phrase. Here the first letter, that phrase will be denoting the first letter of the colored codes. That phrase is B.B. Roy, Great Britain, very good wife. So you can repeat B.B. Roy, Great Britain, very good wife. And the tolerance will be usually about 5% or 10%, and if there is no color in the resistor, that is in the case of fourth ring, the tolerance will be about 20%. And for the resistor which is shown in this 2.12, we have the green color, next blue, and then orange. So the green color shows 5, and the second digit blue is 6, and decimal multiplier orange, therefore that will be followed by 3 zeros. Therefore 56K will be the value of the resistor, having a tolerance value of about 5% as it is gold ring here. And this color code can be written as BB Roy, Great Britain, very good wife. Then we can study about this color coding of the resistor. Using that we can construct many electronic circuits. In this simulation we have a resistor R and another resistor connected in series, and the voltage supplied to this electric circuit is about 5 volts, and here is a galvanometer which shows the current. If we are using these two resistors like this in series and adjust the values of the resistor, you see the value of current in this galvanometer. And where we are adjusting the position of the jockey, the current varies like this. So from the minimum value to maximum value. You can also adjust the value of resistor from 1000 ohms for the first one resistor and for the resistor R, and R1, the second resistor connected here, to about 2000 ohms. We can adjust the value of each resistor to a maximum value of 5000 ohms for the first resistor and for the second resistor also. So we are having these two resistors which are connected in series. Now if we are connecting another resistor, here R is the first resistor, R1 and R2, there are about 3 resistors which are connected in series. Now let us see what happens to the resistance values and the current value. Here the value of the first resistor is decreased to about 1000 ohms, and the second one we can increase or decrease like this, and for the third resistor also we can increase. So in this case, if the jockey position is kept at the maximum level, maximum current will be here shown in the galvanometer, and if you are adjusting the position of the jockey, the current value changes. Similarly, we can also adjust this circuit for resistors connected in parallel like this. So here you see there are two resistors which are connected in parallel, and let us see what happens to the resistance value and current value. Here you are changing resistance value R and R1 value to about maximum of 5000 ohms, and R2 value also about 5000 ohms. And if we adjust the jockey position like this, you see the change in current in the galvanometer.